Hello everyone, this is Professor Roman. Let's continue the group theory lectures. We have taken care of the preliminary information that we need and more, and it is time now to turn to the study of group theory itself. But just to make sure we're all on the same page, I did want to very quickly review two concepts that we will need, of course. Algebraic operations and closure. If A is a non-empty set, then a nullary operation on A is an element of A. A unary operation on A is a function from A to itself. And a binary operation on A is a function from A cross A to A. We also discussed two different styles of notation: additive notation, where the binary operation is denoted by a plus sign and called addition, and multiplicative notation, where the binary operation is denoted by juxtaposition, or one of these notations here with a dot or a star or something similar to denote the product. Also, if B is a non-empty subset of a set A, then B is closed under a nullary operation on capital A, so an element little a of capital A, if little a is also in B. B is closed under a unary operation, F mapping A to itself, if the restriction of F to B maps B into itself. And that can also be phrased this way: F of the set B is a subset of B. As you know, F of a set is the set of F of little b for all little b in capital B. And finally, B is closed under a binary operation, F on A, if F of B cross B is contained in B. So that's what we need, and we are now ready to look at the first definition of a group. This definition is the most common definition. It's the one you will see in my experience, in virtually all books that define groups. A group is a non-empty set G, called the underlying set or carrier set of the group, together with a binary operation on G, often denoted by juxtaposition and called a product, so I'm using multiplicative notation here, with the following properties. Associativity, the product is associative, and the equation looks like this. Identity, there exists an element which is generally denoted by 1 or E in G, called the identity element for the group, for which 1A equals A1 equals A for all elements A in the group. This is the neutrality property that we discussed in an earlier lecture. And finally, oh, by the way, these two properties are enough to make G into a monoid. The third property, inverses, for each element little a in G, there is an element, and this is read A inverse in G, called the inverse of A, for which the product of A and A inverse in either order is equal to the identity. Now, it's common practice to say phrases like the set G is a group under, and then describe the binary operation. For example, the set of non-zero real numbers is a group under multiplication. But it is best to avoid phrases such as the set of non-zero real numbers is a group. I hear that sort of thing all the time from students. In that case, actually, you can figure out what the binary operation probably is, but it's much better to mention the binary operation. It is a really good habit to get into. For example, what if I said, consider the set Z of integers? The set Z of integers is a monoid. Your response to me should be, which monoid? Are you talking about addition, multiplication, some other binary operation? So the set Z of integers as a monoid is incomplete. It's ambiguous. And so you should make an effort to stay away from statements like that. As we discussed, once a binary operation is defined on G, you've shown it's associative, you've shown there's an identity element, and you've shown that every element has inverses. From that point on, since the identity element and the inverses of each element are unique, you don't need to repeat that. You can then you can say G is a group under the following binary operation and leave it at that. The rest is determined and so does not require explicit mention. Now, if you look again at the definition I just gave you for a group, and as I say, it's the most common definition, you will notice that it's not in the true spirit of the definition of an algebraic structure. Remember that an algebraic structure is a non-empty set, the carrier set, together with some algebraic operations that have certain properties. So it's three items: carrier set, algebraic operations, properties of those operations. A group has three operations, but the definition I just gave you only mentions the binary operation. So here is a variant of the definition that is more in the spirit of the notion of an algebraic structure. A group is a non-empty set G, again called the underlying set or carrier set of the group, together with one binary operation on G, one unary operation on G, and one nullary operation on G with the following properties. The binary operation, again, we denote by juxtaposition, call the product, is associative. The nullary operation, denoted by 1 and called the identity element of the group, satisfies this property. The unary operation that sends an element A to an element often denoted by A inverse and called the inverse of A has the property that A times A inverse in either order is equal to 1. So this follows exactly the pattern of an algebraic structure. Underlying set, operations on the set, properties of the operations. But again, the other definition is more common. You won't see this as often as you will see the other definition. Of course, the two definitions amount to the same thing. They define the same algebraic structure, just in slightly different terminology. Also, the formal notation for a group, as we did for monoids earlier, would be to write an ordered quadruple. G, then that's the underlying set, then the binary operation, then the unary operation, then the identity. But quite frankly, this gets to be a little bit of a pain in the neck, I think. You have to think of symbols for the various operations, and it's just not something that I think you see all that often. Generally speaking, what you will see in theorems in this book and in other books is simply they will begin with let G be a group. And that means that there is a binary operation, there is a unary operation, there is a nullary operation. They satisfy the properties of a group, but they're not specified exactly. So this definition is an illustration. Let G be a group. Two elements of G commute if AB equals BA. So you see immediately, without any comment from me, that I'm using juxtaposition for the product. More generally, the elements A1 through AN commute if every pair of these elements commute. So this is pairwise commutativity. A group is said to be commutative or abelian if every pair of elements commute. Abelian groups are, in general, simpler than non-abelian groups. That should be relatively obvious because commutativity is a very useful property. It simplifies things quite a lot. But abelian groups are by no means trivial. A group is finite if the underlying set G is a finite set. Otherwise, it's infinite. We don't often make a distinction between the different cardinalities of an infinite group. I suppose there are situations where that might be interesting or useful to do, but generally we just think of groups as either finite, and then we do care about their size, or infinite, and we leave it at that. The order of a finite group is the size of the underlying set. And we'll denote that by O of G, O for order, or the double bars here, which is the one standard notation for the cardinality or size of a set. And groups that are not finite, or do not have finite order, then, are said to have infinite order. The term abelian is named after Niels Heinrich Abel, who was a brilliant and prolific mathematician and who did quite a lot of work, early work in group theory in the early 1800s. Group theory was advanced quite a lot. Well, I'll mention that a little bit later. But a great deal happened in group theory between, let's say, 1797 and the mid 1800s. And again, I'll talk about that a little more later. Unfortunately, Abel died of tuberculosis at age 26. And it was 2 days before he was to receive a letter from a friend of his who found him an appointment as a professor at the University of Berlin. So it was very bad luck. You might remember, if you listen to the previous videos, we talked about common themes, and I said that after the definition of a widget, you will very likely see some consequences of the definition, some simple consequences of the definition, such as the uniqueness of the identity element and the uniqueness of inverses. So here is that discussion. If you were to have two elements, 1 and 1 prime, that were both neutral for the product, in other words, both identity elements, and you took the product of these two elements, you can interpret this in two ways. You can think, since 1 prime is neutral, this product is 1. Since 1 is neutral, this product is 1 prime. So 1 and 1 prime are equal. In other words, the identity is unique. And that is not part of the definition of a group. Similarly, every element, which we know does have an inverse, because we have a group, the inverse is unique. And I'll let you prove that. I'll also leave it to you to show that A inverse is A, and that the product AB, its inverse, is B inverse A inverse, You must reverse the order of A and B unless you know that A and B commute. If they don't commute, it has to be this. You're familiar with this sort of issue. For example, if capital A and capital B are matrices, if they're invertible, then their product's invertible. Their inverse is B inverse A inverse. It may not be equal to A inverse B inverse. Sometimes it will, sometimes it won't. Same thing for composition of functions. You have to reverse the order of the factors. Now, the presence of inverses permits cancellation in a group. So we can cancel like factors on both sides of an equation. And just to go over that in careful detail, which you have to do the first time. Somebody had to do it, and so we should do it. If we have three elements, a, b, and x in G, and we know that xa equals xb, then we can multiply both sides by x inverse. And I will let you think about why that's okay to do. And the parentheses go here, xa and xb. Now we can use associativity to move the parentheses. Then we can use the property of inverses to write this as 1a equals 1b. Then we can use the property of the identity, a equals b. So in this simple proof, we actually used all the properties of the group operations just to prove that we can cancel. And similarly, we can cancel on the right as well. And it's interesting to note that when groups were first discovered, which I think was probably by Joseph Louis Lagrange, you may have heard of Lagrange multipliers, sometime in the very late 18th century, the notions of associativity, identity, and inverse were not explicitly mentioned. But the first groups, the groups that Lagrange worked with, the groups that Galois worked with, were finite sets of bijections under composition, permutations under composition. And so associativity was evident at the time. Composition of functions was known to be associative, even if it wasn't explicitly mentioned in that language. The identity bijection was there and acted as a neutral element for composition. But the notion of cancellation was used in place of the notion of inverses. And one can prove, that if G is any finite set with an associative binary operation, binary product, and an identity element, so in other words it's monoid under the product, then the cancellation property implies that G has inverses. And we've already seen the converse, and so cancellation is equivalent to the existence of inverses. And I will leave that as an exercise. But by the mid-19th century, about 50 years after Lagrange's initial contributions, group theory had undergone considerable further development. And that was through the work of several mathematicians, most notably Arthur Cayley, Augustin Louis Cauchy. There's a very famous theorem in group theory called Cayley's theorem, which we'll discuss. Also, there's Cauchy's theorem, which we'll discuss. Abel, whom I already mentioned, and Évariste Galois, who is rather well known to many students of mathematics. But the modern group axioms, as I have laid them out for you, the definition in terms of associativity, identity element, and inverses, didn't really emerge until almost 100 years after Lagrange's initial contribution. It was with the work of Walther Franz Anton von Dyck in 1883. He was interested in geometry and how groups related to that. The term group itself was probably not used until about 1831 by Galois. Galois, by the way, as you may know, died in a duel in 1832 at the age of 20. So despite evidence to the contrary, Abel and Galois, there's probably no direct connection between studying group theory and dying young. I'm 72, I've studied group theory, and I'm still alive. So anyway, I'm going to describe for you the way Galois viewed groups later in the book, later in the course. We also discussed notation for binary operations in a previous lecture. Let's go over that very quickly. The multiplicative notation looks like this. You call the binary operation multiplication or the product. Use juxtaposition or one of these other similar notations. The inverse, the unary operation is called the taking of inverses or multiplicative inverses. So A inverse, this notation is for the multiplicative inverse. Nullary operation is called 1 or the identity or the multiplicative identity. And the notation is, I use 1, some people use E. As to additive notation, we use the addition sign, we call this the sum. Inverses are called negatives or additive inverses, denoted with a minus sign, a negative sign in front of A. And the nullary operation is called 0 or the identity or the additive identity. But the unadorned word identity is a little dangerous. It may confuse some people because it is used quite often in the multiplicative notation. And 0 is the notation for the additive identity. It's perfectly fine to use the phrase additive identity, multiplicative identity. That's very safe. To emphasize the notation that's being used for a particular group, the group is often referred to either as a multiplicative group or an additive group. So I will, for example, use the phrase the additive group of rational numbers later on. And these adjectives refer only to the type of notation. There's only one kind of group. It's a question of what notation do you use for it. You can use additive notation, in which case it's called an additive group, or you can use multiplicative notation, in which case it's called a multiplicative group. But the term additive group and writing a group in additive notation tacitly implies that the group is abelian. We do not use additive notation for non-abelian groups. I have to make a slight addendum here. I did see that once, that one rather notable author, as I recall, did say, I'm going to make a very rare exception and use addition and additive notation for a group that is not commutative. I can't remember exactly in what context that was. It was so obscure and I saw it so long ago, I don't remember any details, so I can't point you to that. But it was a rather advanced level group theory book. On the other hand, multiplicative notation is used for both non-abelian and abelian groups. And I'm going to use multiplicative notation in this book, even for abelian groups, except where additive notation is more common, so I will follow common usage, or if it's more appropriate under certain contexts. For a multiplicative group, exponentiation is just repeated product. So a to the 0 is 1. If n is a positive integer, a to the n is the product of n factors of a. A to the negative n is the product of n factors of a inverse, which can also be written as the inverse of a to the n. And I'll let you sort out why that is. When you use additive notation, the role of exponents is taken by multiples. So you have NA, which is the sum of n copies of A, and negative NA, which is the negative of n times A. For small groups, we can describe the group product completely using a table called the multiplication table for the group. So to be specific, if our underlying set contains, of course, the identity A1 through AN, so there are n plus 1 elements in the group, then the multiplication table for this product on G has one row and one column for each element. So here are the column labels, and here are the row labels. And then in the row labeled AJ and the column labeled AK, the intersection is this cell. We place the product, AJ, AK. So this table describes the product of every two elements in both orders. And the table will be symmetric about the diagonal if and only if the product is commutative. And it's certainly not true that every table of this form is the multiplication table for a group. A table like this just defines a binary operation on the underlying set. Only those tables whose binary operation is associative, has an identity element, and for which every element has an inverse will be the multiplication table for a group. So here's a table I whipped up quickly, the identity and two other elements. And this defines a binary product, but it's not a group product because, for example, none of these elements functions as an identity element. It is extremely useful, and we'll use this quite often, to extend the notation for the group product, which is defined on elements, extend it to subsets of the group. So specifically, if S and T are non-empty subsets of a group G, then what I'll call the set product ST is defined element-wise. So capital S times capital T is the set of all little s times little t, where little s comes from capital S and little t from capital T. And so this is just the product of all elements, one from each set. And there are some special cases if we have a singleton set just containing A and another set. Then this set product is usually written just as AS. We drop the curly brackets. So AS is the set of all A little s for little s and capital S. And the same thing when the A is on the other side. Again, if we don't have commutativity, these are going to be different sets. Notice that because the group product is associative, so is the set product. And I'll let you supply a proof for that. It's a very useful property that we will have occasion to use, well worth remembering. Also, the singleton set containing just the identity element of the group functions as an identity for the set product. One S is S, and so is S1. But there's no notion in general of inverses under the set product. So the family of all subsets, the power set of G, fails to be a group under the set product. The set product is not a group product, but it is a monoid, because the set product is associative and there is an identity. So this is another example of a monoid. We can generalize the set product to any collection of, well, let's say finite collection of subsets of G. So if S1 through Sn are subsets of G, then the product of S1 through Sn is just the set of little products. You pick little s1 from capital S1, little s2 from capital S2, and so on. On the other hand, if k is a positive integer, then it's customary to let s to the power k be just the kth powers of the elements of s. And here we have an inconsistency in notation. So we have to be very careful here. For example, s squared is not the same as s times s. S times s is the set of all possible products that look like this. S squared is the set of all squares of elements of capital S. These are not the same set in general. So you would be justified in feeling there's some inconsistency here in notation, and you'd be correct, but it's too late to change it now, so we just live with it.